Hi, and welcome to Statistics 1, Lab 4. The goals of today's lab are to read a data file into R, which we've done already. Again, print summary statistics, which we've done. We'll do correlation analyses, which we covered last week, but then we'll also do regression analyses, which is the main topic of this week. And you'll see that we'll do a regression analyses yielding unstandardized regression coefficients. And then we'll do a regression analysis giving us the standardized regression coefficients. And you'll see it's a really simple manipulation to go from unstandardized to standardized. And the example this week is a little different. It's actually much simpler. There's just 3 variables. So the example is a correlational study investigating predictors of physical endurance in healthy adults. So the outcome variable y is physical endurance. And you'll see that's just on an arbitrary scale that's measured from 0 to 60. And the predictors, the x variables, are age and number of years that the person has been actively engaged in exercise or sports. You'll see that the sample, which consists of 200 people, consists of people who are pretty active. So we'll see that when we look at the summary statistics. Again, I've commented out these lines of code because I know I'm in the right working directory, but just make sure you're in the right working directory. Make sure your data file is spelled correctly. There's been a lot of problems just downloading data files. Just make sure you're spelling your data file correctly. Make sure you're downloading it into your working directory. The only package we'll need for this lab is the psych package. So most of you should have that installed already, but if you don't, if you're joining the class late, you need to install the psych package. Again, I've commented that out because I've already done it. Okay, so let's go. Start by loading the psych library, and then I'm going to read in the data file from that text file into a data frame called PE. I'm hitting Command Return, and then Command 1 to go back to the console, and good. It looks like there's no errors. So let me just look at it. I'll use the view. I'll use the edit function, edit PE. You can use the view function if you like. Let me execute that, and the R editor comes up. If you're working in RStudio, you would have already seen this. This is just a participant ID number, which is common. Just give people an arbitrary identification number. Their age and years. Active years refers to the number of years that they've been actively engaged in sports or in exercise. And endurance, again, is this score on an arbitrary scale 0 to 60, where higher scores indicate greater endurance. So now let's move down through the code for this lab, and let's look at some summary statistics. Let's give us an idea of what's in these variables. So here are the summary statistics. You see that we have 200 subjects or participants, if you like, in this sample. And notice I didn't change participant ID to a factor. I left it in there as integer. So R is reading that in as an integer. If you don't want that in your summary statistics table, you could change that to a factor, which we did last week. So technically, I should get that out of there. But let's look at age. The mean age in the sample is about 49.5 years old. As I said, notice that this sample, they're pretty healthy, athletic, physically fit bunch. They've been, on average, actively engaged in sports or physical fitness for 10.6 years, 10.5 years, at least in the U.S. That's pretty atypical for a group of 200 adults. So that will also help to explain some of the odd correlations that you're about to see, which is why I'm pointing it out. And their average endurance score, again, this scale, you'll see the minimum is 3 and the maximum is 55. This scale is an arbitrary scale that we picked. Again, we just made up data for this. It's from 0 to 60, with higher scores indicating greater endurance. So let's go back to the script, and let's run a correlation analysis. just on those three variables. So I'm doing core, open parentheses, PE, that's the data frame where the data are now, and I'm doing open brackets 2:4 because I don't want to put participant ID in there. I just want the three main variables. So I'll execute that. And here are the correlations. So the correlation between age and active years is positive. It's 0.33 approximately. So the older you are, the more opportunity you've had to be engaged in, to be actively engaged in sports. So that's why that's positive. And you'll notice that physical endurance is not correlated with age. If anything, it's negatively correlated. Again, you might think that's a little odd. You would expect a sort of stronger negative correlation, right? Because as you go up in age, you should be going down in physical endurance. But as I said, this is a sort of unique sample because they're very active. The average, again, for active years was over 10. It's 10.5, almost 11. And you'll see that's accounting for this lack of correlation here between age and physical endurance. So then we have a correlation between active years and endurance, as you would expect. So the more people are engaged in active exercise or sports, the better their physical endurance. So let's go back to the script. As we run larger correlation matrices, I think we did this last week. I like to use the round function, makes it a little cleaner. So I just put round around that line of code, and then that'll just give me 2 decimal places. So it just looks a little cleaner. We could also run the function core.test now that you've been exposed to this idea of null hypothesis significance testing. I didn't run this last week in lab because we hadn't really encountered the idea of significance testing yet. We're going to cover this idea a lot more next week when we talk about the central limit theorem in particular. But we could, for each of these, we could just run null hypothesis significance tests. So that correlation between age and active years, it was about 0.33. Is it statistically significant? Well, if I run core.test, R will tell me. So I can execute that one line of code, go back to the console, and you'll see that R gives me this output. It says we're running a Pearson's product moment correlation. That's what core.test gives as the default. It then gives me a t-value of 4.9. What's called degrees of freedom is df. It's 198. It's the number of subjects minus 2. And again, we'll talk a lot about why it's that number next week and how you get this exact p-value. This p-value is stated in significant digits. So this is like 0.00001. So it's very, very low, which means we would reject the null hypothesis that there's no relationship between age and active years. That says here the true correlation is not equal to 0 is the alternative hypothesis. It also gives a confidence interval, which we'll talk about next week. So instead of reporting just the estimated correlation, remember this is an estimate of the true population correlation based on this sample, some statisticians suggest that we should report confidence intervals. So this is our 95% confidence interval for this correlation. It's about 0.2 to 0.45. You see that 0.33 sits right in the middle of that interval. So this we'll cover next week. The correlation coefficient is known as a point estimate, and this is known as an interval estimate. It's just our best estimate of what the true population correlation is between age and active years. Remember, there's always going to be some error associated with just a point estimate, this 0.33, because there's always some degree of sampling error. Well, how much sampling error can we expect? Well, we try to estimate that by calculating standard error, and that's how this interval is calculated. It's based on how much standard error we have. And remember, standard error is largely determined by sample size. But I'm getting ahead of myself. We'll talk more about all of that next week. Let's go back to the script. We could do that core.test for each of the other correlations. I'll do it for endurance in active years and endurance in age. And what we see is up here, this is for endurance in active years. Again, we get this really pretty high t-value, 4.86, and a very low p-value. That means the probability of obtaining this correlation, given the assumption that the null hypothesis is true, is very low. That's what that p-value means. And again, we're going to get into this more next week. Again, it's about the same magnitude as the one above it. And then, of course, this one's not going to be significant, right? So this one is negative 0.08. It's very close to 0. So the t-value is pretty low. It's negative now because we have a negative correlation. So it's negative 1.12, say, and the p-value is 0.23. So that's not a very low p-value. To reject the null hypothesis, we typically want a p-value less than, say, 0.05 is a typical cutoff value. So here we would retain the null hypothesis, and we don't claim here, or we wouldn't claim here, that there's a significant correlation. Obviously, in this case, it's so close to 0. Okay, let's go back to the script. And just to be sure that we're not violating any assumptions here, because you might look at those correlations and say, well, that's weird. Why do we have, there's no correlation between age and physical endurance? That doesn't make much sense. Let's just look at our distributions. So we'll just run some histograms and look at the distributions. So here's age. We have a large range from like early 20s all the way up to around 80. There's two people up here right around 80 who they're almost like outliers. We might want to consider dropping them out of the sample, but they're not so extreme that I'll drop them out, and they're not going to really affect the outcome too much. Active years looks a little bit positively skewed, right? Which is not unusual for that kind of a measure. And then the endurance looks like a really nice normal distribution. So there's nothing too unusual about these distributions. They look pretty normal. We've got a little bit of a positive skew, maybe a couple of data points that are close to being outliers here, but nothing too extreme. So let's go ahead and run the regression analyses. Those look good enough. So let's run, first, let's run a regression analysis predicting endurance from age. Remember, there's no correlation between endurance and age, so we shouldn't get a significant regression coefficient, but let's run the model anyway just to be sure. So I'm going to call this model 1. I'm using the function LM, that's for linear model, because right now we're assuming linear relationship between endurance and age, and we can check that in the scatter plot. I'm using the function summary just to give me the output that's associated with that model. That'll give us the regression constant and the regression coefficient for age when predicting endurance. And you'll see it'll give us a bunch of other things like model R squared and so on. So let me just run that. So here's the output. I ran this model 1, and here's summary model 1. It gives us a range of residuals, which I'll actually show you on a plot in a moment. But this is the most important piece of the output right here, and what you'll typically look to when you do regression analyses, which you'll do for the next assignment and the next couple weeks when we do multiple regression, when we put in more than one predictor. It gives us our estimates. These are the coefficients. So this right here is the intercept, or in my lecture notes, this was b sub 0 in the regression equation. It's just the predicted score on y when x is 0. So if someone had an age of 0, we would predict they would score 30.8 on this arbitrary scale. Again, age doesn't really correlate with endurance, so 30 should be around the average. I can't remember what the average was, but it should be somewhere near there. And what you see is the estimate for the regression coefficient for age, predicting Endurance is negative 0.08. Its standard error is 0.07. That's just how much of a relationship should we expect just due to chance. So it's about the same as the actual coefficient. So it's not significant. Another thing to look for is this multiple r squared. So in this case, it's just literally r squared, the correlation squared. But when we get into multiple regression, you'll see that this is the proportion of variance in y explained by x or x's, all the predictors. So it's the proportion of variance in y explained by the model. So you'll see that it's 0.01. Only 1% of the variance in endurance is explained by age. They're just not related in this sample. Let's look at another example. Let me just do the scatter plot to show you what it looks like. So there's the scatter plot. On the y-axis I have endurance. On the x-axis I have age. And you see it's almost a flat line. It's just a very slight negative slope because the correlation was negative 0.08. But basically no relationship going on there. Now let's look at two variables that are correlated. So active years predicted endurance. So in model 2, let's again use that LM function, but now let's look at a variable that predicts endurance. So now when we look at the summary, let me go down to the coefficients. This is really what we want to look at, right? Now you'll see that the predicted score on y when x is 0 now is much lower, right? Because if you have 0 active years, then I'm gonna predict that you have a much lower score on the endurance scale. And here is the unstandardized regression coefficient. Okay, remember this is unstandardized, so you can't really think of this in terms of like correlation. This is just for every 1 unit change in active years, so for every 1 more active year, it's the predicted change in the endurance scale. So it's almost a 1-to-1. So for every 1 more active year, I'm going to predict 0.75, not quite 1, 1 point higher on that endurance scale. And is that a statistically significant relationship? Well, yes, because this t-value, which is just the unstandardized regression coefficient, 0.7552, divided by the standard error, 0.1553, that's the t-value, and it corresponds to a p-value of like 0.000002. So really, really low. So yes, I would reject the null hypothesis that there's no relationship. And we could conclude that there's a statistically significant relationship between active years and endurance. Not very surprising. The other thing I want to look at here is the multiple r squared. You see now we're explaining about 11% of the variance in endurance just from active years. Okay, let's go back to the script. We can visualize that in a plot. And here's the scatter plot looking at endurance as a function of active years, and you see there's this nice positive slope. Okay. Okay. Now in model 3, I'm actually going to do technically a multiple regression. I know we haven't really gotten into the heart of multiple regression yet, but just to show you why this example is interesting and what can happen with multiple regression, let's put both age and active years in the regression equation together and predicted endurance from that. And you'll see this is pretty interesting. So now, let me again direct you to the coefficients table. Now if we look at age, we get a relationship of a slope of negative 0.222 or 0.223. But notice now the t-value is negative 3 and the p-value is 0.002. So now, again, using a cutoff of 0.05, and we'll talk next week when we talk about the central limit theorem and sampling distributions, why we use a cutoff of 0.05. But it's a very low p-value. So the probability of getting this slope and this t-value, the probability of obtaining those values, given the assumption that there's no relationship between age and endurance, again, that's the null hypothesis, the probability of that happening, given the assumption of the null, is really, really low. So I reject the null. And now we can claim that there is a statistically significant relationship between age and endurance. And it's because we've taken into account active years, which is also a significant predictor. So now both of them are significantly predicting endurance. And if we go down to the model R squared, you can see we're doing a lot better now. By putting in age and active years together, we're accounting for about 15% of the variance in the outcome. Whereas if we go back up to our old output, if we just used active years and we didn't put in age, we were only accounting for about 11% of the variance. So the model gets better by putting in both age and active years together. And that's the power of multiple regression, which we're going to talk a lot about in the next 2 weeks. We'll be talking about multiple regression. Okay, so let's go back to the script. We can't visualize that in one scatter plot if we had both age and physical endurance. So what we're going to do to visualize model 3 in just one scatter plot, and I did this in the lecture, we can save the predicted scores. Because another way to think of that model R squared is it's the correlation between the predicted scores and the actual observed scores on Y squared. So a way to do that in R, and this is a really handy function, the fitted function, that will give me the predicted scores from the model. So I'm going to create a new variable called predicted in my data frame PE, and I'm going to just put the predicted scores there. Then I'll plot the predicted scores against endurance. And now you see the slope is, it's probably hard to tell, I should have put them maybe right next to each other. This slope is even a little bit stronger than the slope in the previous plot, just using active years to predict endurance, right? Because the R squared was a little higher. So this is just the predicted scores from model 3, predicting endurance. And that's a little bit better than just active years by itself. So that's a way to visualize in one scatter plot this model 3 relationship. Okay, we can also save the residuals, which is a very important lesson and something we'll use a lot going forward. So we want to, if we save the residuals into a variable just called E for error, then I could visualize the residuals. So we should see that I have a normal distribution of residuals centered at 0. And sure enough, that's what we get. So if I just do a histogram of the residuals, they're centered right around 0, because some of my prediction errors are too high and some of them are too low, right? And this satisfies the assumption of homoskedasticity, right? The prediction errors are just sort of randomly fluctuating across that x variable, and some are negative, some are positive, and there's a normal distribution around 0. So that's nice to see. If we save our residuals and plot it in the histogram, that's the sort of thing we want to see. I could then look at the relationship between the the predicted scores and the residuals, and of course, those are going to be orthogonal to one another. And sure enough, if I look at the residuals in relationship to the predicted scores, then there's no correlation there. And that should be obvious. Okay, so I'm almost done with this lab, but I just want to show you how to get standardized regression coefficients. It's real simple. We're just going to run the same exact models that we did up above, except we're going to put this word scale, not just word, but function, scale around each one of our variables. So if I just put scale in front of all the variables in all of these models, then we'll get standardized regression coefficients. And just to remind you that the standardized regression coefficients in a simple regression, and remember it's only in a simple regression, the standardized regression coefficients will equal the correlation coefficient. So just to remind us what the correlation coefficients are, I'm going to run the correlations again, and then I'll run these two simple regressions to show you that those should be equivalent. So this gave me a lot of output, so let me go up. So there we are. Here are the correlation coefficients. I just got that by running the core function again, and I rounded to make it clean. So remember, they're about 0.33 for active years predicting endurance, but negative 0.08 for endurance, or sorry, for age predicting endurance. So in this first model, we used the function scale to get standardized coefficients. Age predicting endurance. What is the regression coefficient? Well, it's negative 0.08, exactly the correlation coefficient. Okay. And then if we go down and look at the coefficient for active years, it's 0.326 or 0.33. Okay, so it's exactly the same as the correlation coefficient when we get the standardized regression coefficient in a simple regression. Now, that's not going to be true when we go to multiple regression. So once we add in another predictor, remember those coefficients can change, and it changes a great deal. In this example, it's why I use this example. It's sort of a nice one. Those coefficients can change. So now, even with the standardized regression coefficients, they're not going to equal the correlation coefficients anymore. So if I run that, and now you see I have a standardized regression coefficient for age of negative 0.22, and for active years it went up a little bit, which is sort of unusual. This is a unique example. That's why I use this. It went up to almost 0.4. So it's now in multiple regression, the standardized regression coefficients, they're still going to range from like -1 to +1, but they're not going to be equal to the Pearson product moment correlation. So it's really important to know that in multiple regression, the standardized regression coefficients will not be equal to the correlation coefficient. In simple regression, with just one predictor in the equation, yes, the standardized regression coefficient will equal the correlation coefficient, but not here in multiple regression. And that's what we're going to do in the next couple of weeks. We're going to do more of these multiple regressions. Just one last thing I want to point out here is notice that the R squared is exactly the same for the standardized solution as it is for the unstandardized. And hopefully that makes sense. All we're doing with the standardized solution is we're just changing the scale of the variables. So the relationships remain exactly the same. And if you wanted to visualize that, you can just plot it. But you can see the p-values, the t-values for these coefficients are exactly the same as before. And this multiple R squared, the proportion of variance explained in y is exactly the same as when we did it unstandardized. Okay, so that's it for Lab 4. That's everything you'll need for the next assignment. Good luck on that, and I'll talk to you next week.